Hello everybody, welcome to Blue Marble Science. The Globebusters, Jeran and Bob, have absolutely no clue how light works. This is going to be Dunning-Kruger on steroids. Jeran and Bob believe the intensity of reflected light will increase all the way to infinity if you get close enough to the thing that's reflecting the light. They even have some Jeran math to prove it. Now, warning. What you're about to see is not suitable for children. They already know better, and if they watch this, they're just going to become confused. So, move your monitors back out of punching range. Don't forget your personal protective equipment, including those oven mitts. And Gladys, are you ready? Let's light this dumpster fire and have some fun. Jeran and Bob recently attempted a debunk of a Sci-Man Dan video where Sci-Man had been critical of their ridiculous lack of technical understanding about how light works and their criticism aimed at the recent Israeli moon mission. Sci-Man Dan had pointed out some of the very obvious amateur mistakes the Globesy twins were making regarding the brightness of the moon. In particular, the intensity of reflected light from a very nearby celestial body. So let's listen to the start of this train wreck as Bob tries to go over the inverse square law and gets it completely wrong.
And you know, I'm also noticing the lack of brightness for the moon. I mean, where's that 64,000 lumens?
Right.
That should be there. It should be absolutely blinding. But it's not. And obviously the sun's, got to be coming from behind it. You've got this placard lit up fairly well, right? But everything seems to be dark. And it's like, well, if it's going to obey the inverse square law of light, then that moon should be absolutely, blinding.
Bob, this picture is made from the lander. And while I can't confirm this, you guys said somewhere in the video that the lander was about 13 miles above the surface of the moon at this point. You, of course, are seeing a plaque on the spacecraft with the moon in the background. Now, the spacecraft is being lit by the sun, just like the moon is being lit by the sun. And you can tell which direction the sun is if you look at that crater just above the plaque. Sunlight's coming from that direction. Now, the moon is not a very good reflector. Only about 13% of the light striking it is reflected. Whereas this nice gold stuff on the spacecraft, which is very near the camera, reflects probably most of the sunlight striking it. Since the aperture of the camera is set for the proper exposure for that plaque, it makes total sense that the moon would appear dark. The moon is 13 miles away. The plaque is a few feet away.
But does the inverse square law work when we're talking about reflective light? No, Bob, it doesn't, especially when you are that close to the object. And we've also got inverse square law work when we're talking about reflective light. No, Bob, it doesn't, especially when you are that close to the object. Does the inverse square law work when we're talking about reflective light? No, Bob, it doesn't, especially when you are that close to the object. And we've also got no idea at the exposure settings of that photo.
Sci-Man Dan, you are a moron, sir. All right, let's look at that. Let's look at the inverse square law. All right. So, and this is actually a better depiction right here. As the inverse square law, basically what it shows is if you have a light source, it does not matter if it is direct or reflected, Dan. It is all it has to have is a source, and whatever brightness it is, it is. Jeran gives an example in another video we're going to show here in a minute that say, let's just pick 100 lumens out of the air arbitrarily. Okay. So what happens is that inverse square law, as the light diverges out, right? You've got original distance, original brightness. But when you double the distance, then according to the inverse square law, the brightness must go down to 25% of what it was. Okay. Now, when you triple the distance, you basically have 9 times the area, and it goes down to 1/9 the original brightness. When you quadruple it, then you're looking at a 4x4 square, or 1/16 the original brightness. Now, as far as Dan's stupid statement that the inverse square law does not act on reflections or return signals or reflections or whatever, the inverse square law applies equally to not only direct light. It applies to gravity. It applies to electromagnetic radiation, EM radiation. And here we have in Wikipedia your God reference, Dan, that says radar energy expands during both the signal transmission and also on the reflected return. So the inverse square law, the inverse square for both paths means that the radar will receive energy according to the inverse fourth power of the range. Meaning, Dan, that it doesn't matter that it is a reflected light. It is still a light source, and whether that light source is reflected or not, it still has a fixed brightness to it. And from that fixed brightness, whether it is direct or reflected, Dan, it must obey the inverse square law, period. Okay. Now there you have some serious Dunning-Kruger from a guy that has the audacity to actually call himself Psi-Man Dan. Yikes.
Well, Bob, Psi-Man Dan wasn't saying the inverse square law doesn't apply to reflected light. He was pointing out the fact that when you get that close to a very large light source like the moon, the inverse square law no longer applies. In the same article that you were referring to, if you had gone down to the paragraph that discusses light, you would have found this sentence. When the illuminant is not a point source, and the moon certainly is not a point source, the inverse square rule is often still a useful approximation. When the size of the light source is less than 1/5 of the distance to the subject, the calculation area is less than 1%. They're saying that if you are more than 5 times the diameter of the source, in other words, 5 times 2,000 miles, 10,000 miles away from the moon, then it obeys the inverse square law. When you're closer than 10,000 miles, it does not. We can show you that in this depiction. If you have an isotropic point light source, the following is true. The luminance, E, is equal to the luminous flux, P, from the source, divided by 4 pi r squared. That's the surface area of a sphere with radius r. That would be like the distance from the moon to the Earth, or to you, where you're measuring the intensity of the light. However, the moon is not an isotropic light source, nor is it a point light source. It's a 3,200 kilometer sphere that is approximately 50% illuminated by the sun. You can see what's happening in this sketch. When you are 5 times the diameter of the moon from its center, like the little red dot on the right-hand side, you're seeing pretty much all of the light that's being reflected by the moon. As you move closer and closer to the moon, you are seeing less and less of the surface. By the time you reach the point that you are 1 diameter from the center, you're only seeing a very small portion of the moon. This is why you can't continue to use the inverse square law, Bob.
All right. So let's go a little bit further. I think this is about all I'm going to do in this, but let's see what else he says really quick. You also got to love that Israel is space ill, like it's sick. You know, their thing crashed. They're illin'. Here we go.
I can't believe he would say that, because I think any kind of search will tell you right away. Just one search, is the inverse square law in effect for reflected light? And of course it is. The light that's reflected to you is going to diminish by the square of the distance. So, I mean, it's the same. You can't just say, oh, it's reflected light, so it's less light. Okay, if it's less light, then that less light will still follow the inverse square law.
Yeah, well, he does worse than that. He says it simply doesn't apply because it's reflected. Right. So I'm curious what he would think does apply if the inverse square law does not, right? And, oh, yeah, that's right. He's going to make even more fun of it because of your statement about how it would be so dark. If it's this dark, literally, now think about this, people. If it is this dark, right, and we know that this exposure is right? It's not a matter of it's so bright that they've got the exposure cranked way down to dim the moon. They've got the exposure correct here, right, because we're looking at the placard on here.
No, Bob, they don't have the exposure correct for looking at the moon. They have the exposure correct for looking at that very bright little plaque It's very close to the camera, you idiot.
And the vehicle itself, and it's lit quite normally, right? So exposure, whatever it is normal. And if that is true for this particular little thing that's reflecting light back, then this behind it, instead of being dark gray, blue, black, whatever the hell it is, would be bright as all get out. It would be so bright, it would be stunning. But if it was actually this dark, this close to it, then if you double the distance, whatever this spacecraft is away from it, it's going to then become a quarter as dark, right? If you double it again, it's going to become like an eighth, right? It keeps going back inversely to the square of the distance.
Keep talking, nitwit. You're going to need one of these to get out of that hole you're digging.
So as you go back each time, and I don't know how far away this was, but it was on the landing approach, so it had to be, fairly close. And what Jeran is going to say is like, wow, if this is so dark here, imagine what it would be like halfway back to the Earth, or even, several thousand miles. It would literally diminish out of our visible acuity, not because of angular size, but we simply wouldn't be able to see it because of the lighting.
Absolutely, yeah.
Yep. But of course, he's going to make a highlight of this point that you said this and act like you are stupid in saying it. But let's listen to this. And it's sitting there completely dark as can be. I mean, I don't know how much faker this could be.
Right. And if you were this close to the moon and it was only that bright, then you could do the inverse square law working backwards, and the moon would be invisible by, 1,000 miles.
Hang on. Let's just go back a second there. What did Jeran say?
Right. And if you were this close to the moon and it was only that bright, then you could do the inverse square law working backwards, and the moon would be invisible by, 1,000 miles. Right. And if you were this close to the moon and it was only that bright, then you could do the inverse square law working backwards, and the moon would be invisible by, 1,000 miles.
Absolutely clueless.
Let alone what?
Yeah, absolutely clueless. You are, Dan. Now, I will admit that it probably would take a little more than 1,000 miles, as Jeran stated, but the gist of the idea is absolutely correct. You wouldn't have to pull back very far at all before the inverse square law would have taken over and diminished the light completely out of our visual acuity.
I think you're going to need a bigger traco.
Yes, you would agree with that, Jeran?
Yeah, totally. No, I was just trying to think, well, we don't know what this distance is supposedly at, but I think, don't they tell us what the distance was? I think that we could probably figure out what that distance is. But yeah, again, double that distance and it's going to be a quarter as bright. And then if you keep doing that, then I almost stand behind my 1,000 miles. But I would have to know what that distance is there. But regardless, you certainly would never see the moon from the Earth.
Right. Well, one thing we know is that it must be close because it's on the descent. Right?
Right.
That's where this was taken. It's on the descent. It's on its way down, baby. So it's unlikely that it's probably closer than 100 miles would be my guess, even though 100 miles and you being able to see the edge of this, it would be preposterous. See, these are the incongruities and inconsistencies that the space agencies give us. If this thing, looks like it would be at least 2,000 miles away just because of how you can see this edge over here. Well, maybe, or 1,000 miles away, but whatever. Right. But we don't know because the whole thing is convoluted, but so let me play this for another minute. Oh, go ahead.
Yeah, I'd have to go back and look what they say that distance is. But I thought if you go back to we're not looking at their video, but when you look at their video, it actually said how far away they were from the moon. I thought it was extremely close. And if you then say, okay, from that distance, and you can call that 1,000 lumens, then you just keep doubling the distance, and then it would be 250 lumens or half the distance, whatever, and then keep going from there. And I think it would be invisible quickly. Is it 1,000 miles? Could it be 2,000 miles? Could it be 5,000? Yeah, sure. If you want to say that I'm wrong about that, but if you're talking about from the Earth, no, you'd never see it.
Right, exactly. And so before we go in a little further than this, let me go ahead and just play this. You guys, we've used this reference before, and I love this video, Jeran, because it's so spot on. But this gives you an idea of how the inverse square law works. Now, what Jeran is talking about here is how much brighter it would actually be as the astronauts are getting close to it. So it's kind of in reverse. Jeran is asserting that it would be so unbelievably bright, on the order of 65,000 lumens, which if you have any idea how bright that is, it's blinding beyond belief. It's kind of like looking at the sun. But so it's kind of in reverse. Instead of that, we're starting with a very dark moon and moving backwards. But here's an idea of how it works. So let's listen to Jeran on this video, and then we'll continue on.
Now, some things could help us determine which distance was more likely to be correct. For example, the inverse square law of light that says that given a certain brightness or intensity, it is inversely proportional to the square of the distance. So if we know how bright the moon is, each time we half our distance, the brightness increases by 4 times. So you see, we can say the moon is 100 lumens, and it doesn't really matter which number we place on there, as the result will be the same. So at 240,000 miles, we have 100 lumens. At 120,000 miles, we have 400 lumens. At 60,000, we have 1,600 lumens. At 30,000, we have 6,400 lumens, and so on and so forth, and so on and so forth, till we get down to 1,000 miles distance. When we're 1,000 miles away from the moon, the lumens should be 6,553,000. So if we divide that by the original 100, we see that from 1,000 miles away, the moon would be 65,530 times brighter than it is from Earth. Is that what we saw? Well, here's some photos from Apollo 17 from 800 miles from the moon. And you tell me, is that moon 65,530 times as bright as it is from Earth? Of course not. So, one thing or the other isn't true. Either we've never been to the moon, or the moon is far closer. What can't be true is the moon is the distance that they tell us, and that man has been there.
Okay, I've got to stop at that point. Jaron's got the moon's illumination completely wrong. It's more like 0.15 lux, not 100 lux. He could have looked this up, but he doesn't want to. He wants to inflate the number as much as he possibly can, which is a fairly dishonest way of doing things, but that's Jeran after all. He's trying to use the inverse square rule all the way down to well under 1 radius of the moon. That's exactly what Simon Dan was being critical of, and what we talked about earlier, and the reason why you can't do that. He's pretending the moon is an isotropic point light source, and it isn't. He and Bob apparently don't comprehend the concept of limits, because the way he's trying to use the inverse square rule, as the distance to the surface of the moon approaches 0, luminous flux would have to approach infinity. What? Obviously, Bob and Jeran are totally clueless about the way light behaves, and clueless about a lot of other things too. Here's where you screwed this up, Jeran. The light source is the moon, and the total luminous flux coming from it is finite. Since the moon isn't a point source of light, the inverse square rule only works when you're a sufficient distance from it, about 10,000 miles. You assumed that r sub x divided by r sub y. Let me explain what that is. Let's say r sub x is the distance from the moon to the Earth, 240,000 miles. Divided by a shorter distance, a closer distance. That squared applies all the way to 0, and it doesn't. By the way, that's the way you do the inverse square rule, Jeran. You don't have to keep dividing by 2. Take the ratio of the 2 distances and square it. It's the same thing. But let's examine what you seem to think. What you're saying is the limit as r sub y approaches 0, of r sub x divided by r sub y squared is infinity. That is totally impossible. If the moon is 240,000 miles away and it produces 0.1 lux illumination, here the illuminance at 10,000 miles is 240,000 divided by 10,000 squared times 0.1, 57.6 lux, not tens of thousands of lux. At 10,000 miles, the angular size of the moon has become 11 degrees. That's as far as we can go with the inverse square rule. I've already shown you why. Let's make a ballpark guess at the surface illumination of the moon. We know the distance to the moon, we know the radius of the moon, and we know the average illumination here on the surface of the Earth. I've rearranged the formula previously to say P is equal to E times 4 pi r squared. But if you recall, that is for a sphere. 4 pi r squared is the illumination coming from a point source, and it's the surface of a sphere. The moon is only 50% illuminated, so I'm going to assume that instead of the entire sphere, it's a hemisphere. So P will be E times 2 pi r squared. The total illumination, therefore, coming from the surface of the moon is 1.4 times 10 to the 17th lumens. That's a huge number. The problem is, that's what is coming from the entire surface of the moon. Now, if we divide that by the area of one hemisphere of the moon, you'll end up with 2,744 lux at the surface. That comports very well with all the published data I can find. Most of the time you see numbers of 2,500 lux at the moon's surface. I've got an old college text that says 2,900, so certainly right there in the ballpark. It surely is not hundreds of millions of lumen the way you had represented it later in this video. So at this point, I don't see any reason to go further with this. What I'd like to do is leave you with three thoughts. Your understanding of light, the inverse square law, and the math associated with it is just plain wrong. Simon Dan was correct. You can't use the inverse square law when the source is 154 times larger in diameter than your distance to it. And that's exactly what you're looking at in that picture. And the third thing I would say is, fellas, try understanding what you're talking about before you start talking about it. Hey, thanks for watching. If you enjoyed it, please don't forget to hit the like and subscribe buttons, and we'll catch you on the next one. Gladys, we're out of here.